So we need to be able to use VSEPR theory to predict molecular geometries. And this is one of those parts of Chem 1A that's very important if you're going on to organic chemistry. This is really important for organic chemistry.
So that 1B?
No, 1B is not. It's 28, 29. So we need to, here are the steps. First, draw the Lewis structure. Figure out the total number of electron groups on the central atom. Determine the number of bonding groups and lone pairs. And this is where I think the book's instructions are just silly. Refer to table 10.1. Well, that's great when you're doing homework. I'm not going to give you that table on an exam. So don't refer to the table. Check your work with the table, but I would recommend doing this. Think about how balloons would arrange themselves, and then imagine that the lone pairs are invisible balloons. And things will go pretty well. Let's do some examples. Predict the molecular geometry and bond angle of ClNO. What do we have to do first?
Lewis structure.
Lewis structure. ClNO. Well, I need electrons, right? Chlorine has 7 valence electrons. Nitrogen has 5. Oxygen has 6. So that's what, 18? So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Is this a good Lewis structure? No, what's wrong with it? Nitrogen only has 6 electrons. It doesn't have an octet, right? We ran out of electrons before we could give everyone an octet. So how do we fix that? Double bond. So we need to take a lone pair either from the chlorine or from the oxygen.
What made you decide to put nitrogen in the middle?
That's a good question. Why did I decide to put nitrogen in the middle? Because it was written ClNO. So I figured I'd try that first. How's that for a fancy answer?
I thought, didn't you say at one point, like, obviously hydrogen's always an end molecule, and then like Cl would be an end molecule because it has 7.
It likes to make one bond.
But then oxygen and nitrogen are kind of reversible, aren't they?
Well, you could draw it either way, but if you draw it with the oxygen in the middle, you're not going to be able to do it with 0 formal charges and satisfy the octet rule.
Gotcha.
Which is not to say that that molecule doesn't exist, because it could exist, but it would be a completely different compound with different properties.
Yeah.
Yes?
Don't we put the most electronegative on the outside?
Usually, yes.
Okay.
Which is more electronegative, nitrogen or oxygen?
Oxygen.
Oxygen,
So it's on the outside.
yeah. And chlorine
Chlorine is also
more electronegative. And so it follows that pattern as well. So we've got, I think what's frustrating to a lot of students about this is I can't give you a hard and fast set of rules about how to connect the atoms. I can give you guidelines like try to make it symmetrical, put more electronegative elements on the outside, but sometimes we just have to come out and tell you put this one in the middle. And the way this one is written, we're suggesting that you put nitrogen in the middle. Okay, so should I take electrons and make a double bond with chlorine or with oxygen? Oxygen, why?
Oxygen likes to make 2 bonds.
Oxygen likes to make 2 bonds, right? So if I do that, it's going to end up with a formal charge of 0, and that would be a nice thing. So we move that lone pair in, and now we see that oxygen has an octet, and it has 2 bonds. Nitrogen has an octet, it has 3 bonds. Chlorine has an octet, and it has 1 bond. Everybody's really, really happy here. If you calculate formal charges, they all end up being 0. So this is the correct Lewis structure. We're supposed to find the molecular geometry and the bond angle.
And then can I ask you kind of a sidetrack question? For the resonance structures, that only deals with bonds, right?
The resonance only deals with moving bonding electrons, pretty much.
So would this have one resonance? No, it wouldn't have it.
Well, you could draw it. You could draw it like this.
But it would
But when you compare the formal charges on these two, you'd find that formal charges are over here. And so about all we've learned about that is that we would predict that this would have much more influence on the actual structure. So this central atom, how many bonding groups, I'm sorry, how many electron groups?
4.
I'm hearing 5, 4, and 3.
4.
3.
Wait, which one?
Nitrogen, the central atom.
How many electrons?
Electron groups.
I thought it was lone pairs and then any bonds.
Yeah, but a double bond is 1. Yeah. Double bond is 1. Single bond is 1. Lone pair is 1. 3 groups. How do 3 groups arrange themselves? Think about balloons. What would they do? They'd make a flat triangle, right? Call that trigonal planar. This is plane is the nice word, fancy word for flat. So this would be just 3 groups, right? And what would we expect the angles to be? 120. Because all the way around the circle is 360 degrees. And then dividing that into 3 equal pieces, each of them would be 120 degrees. So the electron geometry is trigonal planar. We need to know that so we got the trigonal planar. We have 1 lone pair. So what we're going to do is, without moving these, we're going to make one of them a lone pair. So here we've got the lone pair. And then to get the molecular geometry, we're looking at the shape of just the atoms, not the lone pair. What's the name of that shape? It's bent. So the molecular geometry is bent.
Can't you tell that from a double bond too, because it kind of bends it over?
Well, no, you could have this with a single bond also. So the double bond in there, we should probably show the double bond. Let's put the double bond here. Whoops. So we'll make this one the double bond. So double bond between the oxygen and the nitrogen, single bond between nitrogen and chlorine. But there's a total of 3 groups. They make trigonal planar. One of them is a lone pair, so he's invisible, and what's left is bent. Now, what's this angle?
Less than 120.
It's less than 120. The lone pair here is very repulsive, like an ogre living in the forest, right? And so these guys, even though they don't like each other, they're going to get a little close together because that guy I hate is better than the ogre, right? So it'll be less than 120 degrees. And there's our answer.
And why is it less than 120?
It's less than 120 because the lone pair is more repulsive. It takes up more space, and so it's going to push those two together. Okay? Yes?
So for an exam, would you put an answer like that?
Yeah, that's a good question. How would this come up on an exam? So this would probably be a multiple choice question. And so 120 might be a choice. 180, 109.5, 90. Those are all angles of specific structures, right? And then maybe there'd be one that's 107, maybe one that's 118. So when we're looking at less than 120, we're looking at a little bit less than 120, okay? It's not going to be a whole lot less. So it could come up like that. Does that make sense? Predict the molecular geometry of I3 minus. 3 iodine atoms bonded together. Well, there's really only one way to put those together. Just put them in a line, right? How many valence electrons do we have to work with here?
Minus 1, or plus 1. So
21
2.
plus 1, right? 3 nitrogens, no, there aren't any nitrogens. 3 iodines, each have 7. So it's 21 electrons. The negative charge is there because it's got 1 extra electron. So we're looking for 22. Got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Where should I put the extras? Maybe the center. Let's try the center. So let's check formal charges. Oh, and we should probably finish this guy off by putting brackets and a negative sign. So this iodine atom, iodines have 7 valence electrons, and in this molecule, if we broke all the bonds in half, it would have 1, 2, 3, 4, 5, 6, 7. So this has 0 formal charge. And this one has 0 formal charge. And let's look at this one. It has 7, came in with 7, and now it's got 1, 2, 3, 4, 5, 6, 7, 8. So that would be a negative 1 formal charge. But we have to have a negative 1 formal charge because of this negative 1 charge on the ion. So it's probably reasonable to stick the extra pair of electrons in there. What would happen if I stuck the extra pair of electrons on one of the other ions, iodines? Well, it would be lopsided. Here, let's try it. Let's stick them over here. Now this one is 7 minus 2, 4, 6, 8, 9. This is negative 2. This one's going to be positive 1 now. And that one's going to be 0. So lowest formal charges are achieved by sticking it in the middle. Okay? How many electron groups around this central atom? 5. Each single bond is 1 group. Each lone pair is 1 group. 5 groups. What do 5 groups do? Trigonal bipyramid. That's not what I wanted. So we got that one guy in the middle, and we got this guy out on the side. And we've got that guy going back, and this guy coming out in the front. So this is the, this is the head, and the feet, and the tutu, okay? So the electron geometry is trigonal bipyramid. We have how many lone pairs? How many lone pairs on the central atom? 3. 1, 2, 3. Those need more space. This is one where the angles aren't the same. These angles are 120, and these angles are 90. So we're going to put the lone pairs in the skirt here, around the equator, because they have more space there. What's the shape that the atoms make? It's linear. So this is linear. And it doesn't tell us to say what the angle is, but what would the angle be? 180. Any questions?
Why did you do the non-bonding
The lone pairs?
lone pairs on the outside?
I put the lone pairs around here because they have more space.
Okay.
Because they take up more space, and so we're going to put them where there's more room. Here they have 120 degrees instead of 90 degrees.
And that's the same thing as a non-bonding.
Non-bonding or lone pairs, yeah. And, you know, if you did this with balloons, the lone pairs would be like bigger balloons. I just thought of that. It would be like jumbo balloons. And so, you know, you could squish them around, but they're going to want to revert to this arrangement because if this fits better, there's less strain. Okay. Any other questions? So you don't need the table to do problems like this. All you have to do is think about balloons. Balloons are happy, right? Except when they pop. I don't like popping balloons. So how to represent these three-dimensional things on paper? Well, some of the things are two-dimensional, and they're a piece of cake. Linear is fine. Trigonal, planar, square, planar, bent, no problem. But these three-dimensional ones are tricky. And so what we do is we use this solid wedge to indicate something that's coming out of the plane of the paper or the board or the screen. And the hatched wedge or the dashed wedge to mean something that's behind. It's like a dotted line is behind because you can't really see it. And it takes a little bit of practice and maybe a little bit of visualization. Tetrahedral is the one we have to draw the most often. And so if I'm drawing a tetrahedron, these three atoms can be in the plane of the screen. But then there's going to be one that's kind of sticking out at you, and then there's one that's behind. If the screen was opaque, you couldn't see that one behind. Does that make sense? Someone should come up with a 3D app for this so that we could look at this and have it jump out at us. Any questions?
Don't we all have like 3D glasses in class?
That would be cool, wouldn't it?
Like a 3D projector?
Yeah, 3D projector, and we could have the molecules going around and doing stuff. It'd be really fun.
Except for maybe like the production slides themselves.
Well, that would be a little bit difficult. And we'd have to do the new type, not the
That's a great idea.
red-blue, because that doesn't work
More involved.
for colorblind people. Yeah,
Wait, colorblind people can't see 3D glasses?
3D does not work right for colorblind people. I had
Even
four.
the new ones that are clear?
The new ones work okay, but the old ones, yeah. My oldest son is the only one who had been to one of those 3D movies, but he's a little bit colorblind, and he's like, it just gave him a horrible headache because it didn't make sense to his brain. What if you have a bigger molecule and you don't just have one central atom? Give up. No. So this is the molecule glycine. It's an amino acid. And it has 4 central or interior atoms. It's not really right to call them central because that means the one that's in the middle, right? They're interior. They're on the inside. So what we do is we look at the geometry around each of the interior atoms separately. So this nitrogen, we look how many electron groups?
3.
Nope. 4. 3 bonds and a lone pair. 4 groups. How do 4 groups get away from each other? Tetrahedron. Makes a tetrahedron. The lone pair means that one point is invisible. And so that's a trigonal pyramid. So this has a trigonal pyramid shape. Here, the lone pair is sticking out behind, and these are coming out at you, like that, right? We look at the carbon. How many electron groups on the carbon? 4. How do 4 things get away from each other? Tetrahedron. So this has a tetrahedral geometry. So we see this bond and this bond are in the plane, and this hydrogen bond is coming out, and that one's going behind. Hang on a minute. Let's look at this carbon. How many groups? 3. How do 3 groups arrange themselves? Planar, trigonal. Trigonal, planar, right? So 3, it's a flat triangle. Are there any lone pairs? No. So it's just trigonal planar. And so here's that carbon and the double bond with this oxygen, single bond with that oxygen, single bond with this carbon. That is a flat triangle in the plane of the screen. This this oxygen, sorry. How many groups on the oxygen? 4. What do 4 groups do? Tetrahedron. So tetrahedron, and 2 of those points are invisible. So what's left? It's bent. Bent can also be drawn in 2 dimensions, and so here we have the oxygen bent.
How did you get the bend?
I got the bent because there's 4 groups. That's a tetrahedral electron geometry, and then make 2 of them invisible.
Oh,
Okay, and what's left is called bent. Any other questions? So let's look at this one. It says, this is acetic acid. Predict the geometry around each interior atom and make a sketch of the molecule. I won't make you do that on an exam because I don't want to have to look at it. There's time enough. If you go to OChem, you can learn how to draw stuff there. Is this a Lewis structure? No. So we really need the Lewis structure. So I'm just going to copy down what they did give us here. So there's the oxygen, and then we know there's a bond to the hydrogen. And this C with the H3 on it means that there's 3 hydrogens attached to that carbon. Now, you should go ahead and add up all the valence electrons and make sure you've got the right number, but I don't want to take the time for that right now, so I'm just going to finish it for you. That's the Lewis structure for that one. So we need the electron geometry, the geometry, we should assume molecular geometry. The molecular geometry around each of these interior atoms. So this carbon, what's the molecular geometry around this carbon? Tetrahedral. So that one is tetrahedral.
And that's because there's
4 groups. There's 4 groups and none of them are lone pairs. How about this carbon? Trigonal planar. Because there's 3. So that one, and again, no lone pairs. So trigonal planar. And what about that oxygen? Yeah, it's got a tetrahedral electron geometry. It's got 4 groups. But then you make 2 of them invisible, and so what you've got left is bent. So, we're supposed to make a sketch of it.
in mastering chemistry, will it ask us to make aesthetic sketches?
I don't think mastering chemistry asks you to draw. It'll make you do Lewis structures and stuff. It could possibly make you do the wedges. It could do that. But yeah, it's not going to have you actually just freehand draw. So what I'm going to do to draw this is I'm going to make it as easy as possible on myself. I'm going to arrange this molecule so that it is as linear as possible. I had one. I made this one yesterday and somebody took it. Hang on, I'll make it again. So here's the model. And the thing is, those bonds, those single bonds, can twist and rotate. This double bond can't. Right? That one's just kind of stuck. But like this part, the CH3, that can spin around. I can draw it any way I want. It doesn't say what I have to do. So what I want to do when I draw it is I want to line it up so that as much of it is in a plane as possible. So I can get all but these 2 hydrogens to be flat in one plane. That's going to make drawing it much easier.
Are those the double bonds?
Yeah, that's a double bond because there's 2. So I'm going to do that. So here's oxygen to hydrogen. Come on. And then that's going to be about 109.5 angle. And then there's going to be this carbon here. And then that's got a double bond. Nope, that's not the right angle. It's more like this over here. So that's the other oxygen. And then this bond. See, this is 120-degree angles here. And we've got another carbon over here. And then we've got a hydrogen down here. And then I've got one of them sticking out. And one of them kind of going behind. So that's the representation. Come on, move. It's like that. Any questions? Oh, sorry, I had it backwards.